Yeah, so we're gonna start with chapter 6, right? So because I believe that it's also gonna be having a lot of marks there, as you have seen that. So what we're given here in this chapter, from this we're gonna be looking at the types of regions. Then we look on how to sketch an integral. Then we look on how to integrate, which I believe that we all know how to integrate, but then still I'm gonna be giving you a revision on that. So when we come to the integration over a rectangle, so on this one I'm just gonna give you the ways which the rectangle can be written, right? This rectangle thing can be written. So on this one, they can give us an equation like this. Let's say they can say we should find the integral, then they give us r to be this, or they give us r to be, they can say r is this. They say that x is between this, you see right there. So these two are one and the same thing. So with this one, you can interchange these two and still get the same solution, right? Because there's no any equation here, so they're all numbers, so you can be able to interchange and get the same solution. So if we look at let's look at the first question that we have. We can look at the first question that we have. We are given this question, which I think they just gave it to us like this. When you're given this question, right, let's look at this question. We're given this question, they say we must integrate this question, which here we realize that what's inside it's dx. So it means that anything that has to do with y will be taken as a constant, right? And then we can start by integrating this 3. So when we integrate that, we're going to take this out as a constant like we did here. Then we integrate this. When we integrate this, we're going to say this will be 3x 2 plus 1 over 2 plus 1, which this 3 will cancel the 3, right? We'll be left with x to the 3, which is this. Then in this case, we don't even have to show this step, right? We can just move to say this is x to the 3 over 3. And then we cancel that the intervals are from 1 to 3. So we have this. Now we just know that from here you just have to substitute your 3 minus 1. So I believe that with this, everyone knows how to integrate. The first part was just, they were just showing you how do you integrate, how do you treat this as a constant. So we know that we're going to be doing this. Now, when we come to this, right, we're going to have this case. And we know now I want to show you, we know that when we integrate this one, let's say first I would take out 26, 0, 2, I'm left with e 3 to the y dy. When I integrate this, what you're going to do, you're going to say that this is 26, you keep e to the 3y, you divide by the derivative. Since this is with respect to y, so I'm going to do that with respect to y. Derivative of the exponent times ln base. So right, that's how you integrate that e. Then when we come about it, we're going to get that the derivative of this is 3. So we're going to have 3 down here. Then we're going to be left with e 3 to the y. And this is 1. All right. Then this will be 0 to the from 0 to 2, which is this. So if we know how to integrate it, these ones will be simple. So again, here's what's going to happen. Here we're just going to substitute 2 and also minus 1. So this will be 26 over 3 e to the, if I substitute 2 there, I'm going to get 6. Let me say minus 26 over 3 e to the 0 will be 1. So this will be the case, right? So I can even factor out this, which this will be the case. I'm sure if we check, that will be the case. Or yeah, you can even do this at the end. This is how you do it. You're going to say you cross multiply this and that, then you do that. Or actually, I think yeah, you're not gonna even cross multiply because this is the same base. You're going to subtract. So you're just going to say 26 e to the 6 minus 26 all over 3. You can do that for you to get these, right? But you can leave it in how you want. You can leave it here, you leave it here. So what I'm trying to show you here is that since we know that the solution is going to be this, even if we come here, remember these have no restrictions. This kind of integrals have no restriction. The first integral was starting from 0 to 2, right? So now we can start this from 1 to 3. Let's say you have difficulties integrating the first function, right, that they had given you. You can swap that. You can swap that. You just swap them. Then you have this. Then you know that what's going to come inside now, it's dy. Then you have dx outside. These are still going to give us the same solution, because what I'm going to have first, I'm going to have 3x squared outside. Then I integrate this. It's going to give me e 3y over 3. This 3 will cancel out. 0 to the 2. The x. And this will be from 0 to 1. And then I'll have x squared, which won't contribute anything. E to the 3, that is, will be e to the 6. Minus, this will be x. Let me see, x squared to the x squared e to the 0. It's right, which that e to the 0 can just be 1. Then I close that. Then I can just integrate this one. We say right. So with this, it will be simple. If I take this out, then I start integrating. So it means that from here, I can get, let me see, and this will give us, and this will be the integral. If I integrate this, I'm going to have e to the 6 outside. It will be 0. No, let me just integrate it sometime. If I integrate that, 3 over 3, that's x 3 over 3. And this will be 0 to 1. 0 to 1, and that would be e to the 6. And then if I plug 1 there, minus 0, I'll get 1 over 3 minus, this will be 1 to the minus 0 will be 1 over 3. Then I can have e to the 6 minus 1 over 3. Then that's see the final solution there. This one was what, 26 e to the 6 minus that. This one at the end, let me see if we did. I think we might have forgotten this one, right? Because of the same. Let me check here. So usually in this case, it's supposed to be given as the same solution. Let me see. This is 0 to 2, 1, 2, 3 e to the that. And then this is gonna be 3. What's 3? Oh yeah, it's supposed to be 3-ish. I mean, I used the wrong thing. It's supposed to be 1 to 3, not 0 to 1. It's supposed to be giving us the same thing, 1 to 3. Then it means that this should be, let me erase this. It's supposed to be 1, 2, 3. I'll just direct substitute that 1 up until 3. Then when I substitute that, this is gonna be e to the 6, 3 to the exponent 3. It's gonna give us 27 over 3 minus, maybe I can even take out over 3 as a constant, right? And then 27 minus 1. 3 to the 3 is going to give us 27 minus 1 to the 3 will give us 1. Minus here, this will be 27, or take out 1 over 3 as a constant, minus 1. And this would be 26, so this will be 26 e to the 6 over 3 minus 26 e to the 3. Yeah, 26 over 3. So when I factor out this and keep the bases the same, I can see that the base is 3, right? So the base factor out 26 there, I'll be left with e to the 6 minus 1. Or I don't even factor out, I was still going to get the same solution. You see, right? So with these ones, even if you can change the integrals, there won't be any difference as long as all the intervals are constants. So now it means that we can go to the Fubini's theorem, right? Because these ones, they were just giving you a revision here to say this, if you do this and do this, it won't give us any change. So now we come to Fubini's theorem, which what we were doing there was part of Fubini's theorem. So you need to know how to state Fubini's theorem, because they can say state Fubini's theorem. You said right. So you need to know how to state Fubini's theorem. So we know that if f is continuous on the rectangle, which this is how we write the rectangle. If f is continuous on the rectangle, then it's gonna give us the equation, and we show that even if we interchange these two, they're going to be the same. That's what Fubini's theorem says. You see, right? As long as f is continuous, you see, right, on that rectangle, then when we use that rectangle, we can write them in two ways. You say that if we take the double integral on this rectangle of a function, dA will be equals to, from a to b, c to d, dy dx, which can be the same thing if we interchange these two. That's right. That is Fubini's theorem. So what we applying there was Fubini's theorem. So you need to know how to state it. You just need to know how to write this statement from if f is continuous up until here. That's right. So once you know how to write Fubini's theorem, then we'll be good to go. So you'll be given questions in this scenario. They say you must evaluate this, where the rectangle is this, right? So every time you write such a question, don't just start and say that the integral of this, you start solving. You must start from where they asked the question, like here. So you must say that this is equal to this. So in other words, you can start anywhere here. Someone can decide to start and put these two intervals, and someone put these two intervals. But you must know that when the rectangle is given to you like this, these ones are going to represent x. These ones are going to represent y. You see right now. So this is what you must know. That's why here we had 0 to pi over 2, which is outside. You see, it's representing x. Then you have 1 to 2, which represents y. It's inside. So that's the only thing you need to know here, that these ones are gonna represent x, this, and these ones will represent y. And then let's see, after putting them like this, we realize the one that is inside, it's for what? It's for y, and this one doesn't have y, so it's a constant. So it means that for us to continue here, we're going to take this out as a constant. We integrate cos. Integrating cos is simple, right? This is how we're going to integrate cos. Remember yesterday I wrote what? I wrote this. I was like sin x cos x minus sin x minus cos x. I don't know if it was, I think it was not yesterday. I think, yeah. Last time we had, I had written these ones like this. I said that when you derive sin x, you get cos x. When you derive cos x, you get negative sin x. When you derive negative sine x, you get negative cos x. When you derive negative cos x, you get positive sine x. But when you're going to integrate, in other words, you're reversing. You see that? So here we're integrating what cos x. It means that I was reversing this back. So I'm going to get positive what? Sine x. So this is just to determine are you going to get a positive one or negative one, right? But going to derive sine or cos, when you integrate, not derive, when you integrate cos of 2x, what you're going to get is sine over 2x over the derivative over 2x. You see that, which this will be sine of 2x over 2. Remember, when you derive this, you keep this, you derive this. When you are deriving this, you derive it, you multiply by derivative of the inside. Here we are integrating, so it means that we must divide by the derivative of the inside. You see, right? So we must divide by the derivative of the inside. So in that case, we see here why when we are integrating this, you see that when we are integrating this cos, we see that when we are integrating a cos, we realize that we are going to say sine of xy divided by the derivative of xy, and x is a constant because here we are doing that with respect to y. Then when we derive y, we get 1. So that is divided by x. So everything from there would be simple. This will just cancel this. All right. Then you start applying this 2 minus 1. So that will be sine 2x minus sine y. Not sine y, but sine x. Then you go in and integrate. I've shown you already how to integrate sine 2x. I've shown you already how to integrate sine x. When you integrate sine x, this is what is... when you integrate sine x, you're going to get negative cos x. So that negative there will multiply by the negative to become positive. You see, right? And then to be like that. So now when it comes to this, right? So there you were just going to substitute afterwards, right? So I don't see the use of showing that substitution. So these are simple as long as that my focus is not here. As long as you know how to integrate, you'll easily get there. And here you can interchange this, right? Interchange this, you get to the correct solution. So now we come to, let me see, any problem that we can work with. Yeah, you can try to write this exercise. It's simple also. You're just going to start from here to here. If you don't like that case, you can do the other one, but it's best here to start with the one that is x, right? Like for example here, let's see, we have the integral r x over 1 plus xy dA. This will be equal to the integral from 0 to 1, from 0 to 2 of x over 1 plus xy, and the one which is 0, 2, I said it represents y, 0, 1 represents x. So this will be dy dx, because this one is inside, right? But integrating here with respect to y, it's gonna be a bit difficult, right? Because y is in the denominator. So it's best if we just interchange this to x. But still you can use y, right? And then you do your case here. You can use n, so you can do this. Any that is difficult, any that is simple to you can use n of this. So this will still give us the same thing. So you can try out on how you're going to integrate this. So we feel like integrating with respect to y is going to be difficult, just change it. Integrate with x. If x is difficult, you use y. So it's up to you there. Also, this one, you do the same thing. So when we check here, in this case, they integrated with respect to y because they knew that if it's in that case, you must use what? U substitution. You change this to u so that it can, when you derive, you see if it can cancel x. If it cancels x, then you're good to go, right? Here with respect to y. So when I derive this with respect to, I'm going to be left with x. That x is going to cancel this x. Then I use ln in this case. It will be 1 over u. Integral of 1 over u is ln u. Then I come back to substitute the u. You see, right? Then, with this being the case, so I'm not going to look at this example. It's just a simple integration. So now my focus is on a general region, right? On how to integrate if you're given a general region. So remember, I said that the moment you see x here on the interval, on these intervals, this is step 1 region. This is step 1 region. You see right now, this will be type 1 region. And so you must know how to also write this. You see right, they can say state type 1 region, state type 2 region. Remember, they can ask you anything, so it's better to study with understanding, right? To know that this is how I write type 1 region, type 2 region. And they both happen, for Binet's theorem and this one, they happen both when f is continuous on a certain region. Here it's continuous on region D, such that D is also that. You can also change the region, say region R, you can use any region, right? And then, so in this case, we know that when we see x there on the intervals, or we see x here on these intervals, that will be type 1 region. You see, right? So always when you write this, when you put this in this integral format, these ones should always be inside. You see, right? They should always be inside. You start with them, then you end with the ones of constants. So when we look at type 2 region, type 2 region is just y on the interval. You see right now, that is a type 2 region. The moment you see y on the integral, you must know that this is type 2 region. So it's not that difficult. It's going to be that. So here we're just only going to focus on type 1, type 2. How do we transition from type 1 to type 2? We can transition using a graph. Graphs are used to transition from type 1 region to type 2 region. And then you can also transition without graphs, as we looked at the first recording. If you haven't watched that recording, it means that you'll have a problem, right? So now we come to this. We are given this question. They say we should evaluate this. They say evaluate this where D is the region bounded by y equals to x plus 2, y equals to x squared. First, you need to draw the graph. This is a area between two regions. You're between two graphs, right? Bounded by the region bounded by those two graphs. So this is just here. They're just giving us a revision from SMTH, right? 011. So or 000 if you did 000. So this is just a revision from those regions where you used to check the area and so on. So how do you draw the graph? I would prefer that you can draw two graphs separately if you want, or you draw one graph at a time. Let's say I start by drawing this one. This one is simple. The graph is straightforward. We know that this is the graph. You see right now, this one without any points. We can just draw that graph without any points. And then we come now. For us to know the graph of this one, right, we must try to check where are these two graphs. Where are they? Where are they intersecting? So for us to check where they intersecting, we must equate them. We're going to equate. So this is x squared equals to x plus 2. Then we take this to the other side. Then we factorize, right? When we, let's do that and see, this is x minus 2x plus 1. So this is x equals to 2 or x, let's say this should be, yeah, x equals to minus 1. So we check that they're going to intersect where x is 2 and x is minus 1. So now I want to check that. So we say that this will be, I'm going to plug on any of the graphs, right, for me to find the solution. So I can plug on the one of x squared. When I plug, when x is 2, y is going to be 4. Because when I plug 2 here, I'm going to get 4. Also, when I plug 2 here, I'm going to get 4. You see right now? And when x is minus 1, y will be 1. When I plug minus 1 here, I'm going to get positive 1. When I plug minus 1 here, I'll get 1. So it means that these two, they intersect where x is 2, where y is 4. Where x is minus 1, y is 1. You see, right? So I know that these two are going to intersect when x is 2, y is going to be 4. When x is minus 1, y is going to be 1. So I know that they will intersect on the upper part, right? So now I check this for this one, right? Because this one was simple to draw. Now I check here the x-axis and the y-axis of that graph. So for the y-axis, I'm gonna let x to be 0. Then I find that y is 2. When x is 0, y is 2. So this is where, on this axis, this is where the graph is gonna pass. You see, it's like already I know that they're going to intersect, and then I know that the graph is gonna pass here. So already I know it's gonna move like that, but I'm just gonna look for these points here because I know it intersects also here. Then I check for the x-axis. For the x-axis, I let y be 0. So I'm gonna have x plus 2. Then I know that the x will be minus 2. So when x is minus 2, y will be 0. You see, right? It's gonna pass there. So I write those points, and here obviously this one is when this is 0, 0 for the graph of x, for the graph of y equals to x squared. So now I have this. I know that the region is here, the region of boundary, and my focus now. Let me erase the blue graph. So my focus now would be to know which graph is the upper graph and which graph is the lower graph. You see right now? That will be to know which one is the upper, which one is the lower graph. So that will assist me to know this. This is the lower graph, x squared, so it's going to be less here. So I'm just going to write my y. You see right now, I put it in between. Because you see here, they both share something in common, which is y. So I put y in between. The lower one is x squared. The upper one is x plus 2. So it means that x plus 2 will be bigger, x squared will be less. Then when I come to find the area, this will be from here to here. You see right now? So I'm just going to write the x values. So x was minus 1 till 2. You see right now? X is minus 1 till 2. So I know this. So I'm going to take the upper graph minus the lower graph. That will be x plus 2 minus x squared. Then I see that this is going to be with respect to x. That's right. Now if we check that here will be used here to say that this one, I was going to use this to be from 1 up until 2. And this is x plus 2 minus x squared. So now we know that this is what we learned in SMTH, right? So now we're going to write this in a region. So this one, there's no need for you to write. This will just for you to check. This is the upper bound. This is the lower bound. So someone can use this equation to check. If you find that this area that you find here is valid, therefore you are correct, right, to say this. So there's no need for you to confirm this. You can just take this in a region. So when you put this in a region, you're just going to take this as erase, right? Let me erase the blue one. Since here we're dealing with multiple integration, right? So we're just going to do this. Since we know that this is true, right? So we come and do this and write the region. Here we spoke about which region, D, right? We spoke about D. So we'll write this region, then we'll decide which region is this. X1. Already we know X is between 0 and 1. It's between -1 and 2. So we know that X is between -1 and 2. And we know that Y is between X squared and X plus 2. So this is type 1 region because our X is on the interval. You said right now, this is type 1 region. The question is, how do I go to type 2 region? How do we go to type 2 region? Who can tell me, how do we go to type 2 region? Or can we be able to integrate in type 1 region? Like here, we were not yet sure, right? Let's just put our integral and see if we can integrate. If you can integrate, there's no need for you to move to another region, right? So we know that the integral d, this is 6x minus 2y dA will be equals to minus 1, 2 x squared x plus 2 x minus 2y 6x minus 2y, right? Yeah. Then what's inside is the one with respect to y, this one, the one which is outside with respect to x. So let's check if we can integrate this. You see, we can easily integrate this. This one will give us 6xy. This will give us minus y squared. You see that because minus 2y squared over 2 will cancel the 2. So you see that it's simple to integrate. For this one, we don't even have to think twice. We can just use type 1 region to integrate this. So since we know that here we're just going to use this here, they didn't even bother change. Use type 1 region to integrate, they get to the solution, and it's that, right? Then that will be as simple as that. So you can just draw your graph. So those who want to know, usually in most cases for a type 1 region, we point up, but we're going to confirm that, right? We can check, we'll be checking the algorithm together on how do we shade the type 1 region. So those will be confused too. When do I point the arrows up? Because when you have to change the region, now you can point the arrows sideways. You say right now. Then once you know this is type 1 region, this is type 2 region, it will be simple with that. So now we see for this one, it's type 1 region, the arrows are pointed up. So we're going to look for the one which is type 2 region or another type 1 region and see if the arrows are still pointed up. So now we come to this one, right? They say, okay, here's the other question. They say find the volume of solid under the parabola. So this is just the inside equation which they want. And under the parabolic, z equals to x squared plus y squared, and above the region D in xy plane, bounded by the line y equals to 3x, y equals to x squared, x squared. The graph of x squared, you remember it's simple to graph, right? Then we just first gonna draw this one. Then for us to draw the other one, I said that we're gonna equate them and see where they bounded. You see, right? Here, at least they equated them. For us, we equate x squared equals to 3x. Then we solve for x. We found that x is 0, x is 3. So we check when x is 3, y will be 0, y will be 9. So I know that this will be where they intersect. So I would come, I know that now this is going to pass through the center. It's going to pass through here. So here, those are the only, if it also intersects with the x-axis, or with the axis, that is the only part where I have to check, right? I don't have to check any other x-intercept, y-intercept, because already I see that it's going to pass there. So I just draw the graph to pass there, right? Then I check. So now let's draw this. Now when we realize, right, we have this x from 0. We have this x from 0 up until 3. Here we know that x is from 0. X is from 0 up until 3, right? And we realize that this one it's x squared, this one is 3x. So this is the lower part, this is the upper part. So this is 3x less or equals to y less or equals to x squared. This is still type 1 region because x is on the interval. You see, right? So it means that I must point up again. You see, right? Ne? You don't just guess to a point up, point down. As long as x is on the interval, that is type 1 region. So we point up. So now we know that type 1 region, did they use d there? Yeah, it's d. Type 1 region will be d is equals to, we say xy, x from 3, you're from 0 till 3, and then y from 3x till x squared. This type 1 region. We agree, right? Ne? So we draw that. I said that before we change it to type 2 region, we're going to draw and check, can we be able to integrate this? We don't just change, right? Let's see. They said there it's x squared plus y squared. The one which is inside with respect to y, outside with respect to x. It's also going to be simple to integrate. This will just be x squared y. This will be y to the 3 over 3. It's right. It will be simple to integrate. There's no need for us to change to type 2 region. So we'll just do this and we'll keep it this way. So now, since we see that this is going to be simple, if you have a question, guys, make sure to open your mic, right? Then you say what you want to say, because the comment section, I can't see them. Yeah.
Okay, sir. When you're doing the bound for y, ne?
Yeah.
So this, are you not looking for the graph, like looking based on the graph or which one is it below, which one is up? Like now when you're drawing this graph,
x squared is below, right? Yeah, minute there, I thought x squared was above. X squared is below. It's supposed to be like this, right? Ne? Yeah.
Yes.
Yeah, thank you for that. I thought it was I don't know why I considered it to be above, so it's supposed to be this. So thank you. So it means that now when we go, we're going to have this case, right, which will be the type 1 region. And then then it means that now you know that you can be able to integrate this, right? So there's no need for you to interchange the integrals, the regions. But if you want to interchange the regions, I specified it yesterday. How do we do that? So let's see how we do that, right? Then we know that this is the first region, type 1 region. So for us to write the type 2 region, we're going to say this: d is equals to x, y. Then we say this, we want to change this to y, right? Because there was x there. So I'm just going to put this. Then this one will be x. So to find these ones for y here, it will be simple because already we have the equation here. You see, right now? So we have this equation. So for us to find that lower part, we're going to plug here. When x is 0, what do we find here? We find 0, right? When I plug 0 there, here, I find 0. When x is 3, what do I get there? What is 3 times 3? 9. We agree, right now? Then, now let's check this one. This one we have this. Then when we root both sides, this will be x less or equals to root of y. Then this one here will be, this is y less or equals to, this one is 3x. When we root both sides, no, not when we root, man, when we divide both sides by 3, we're going to get that y over 3 is less or equals to x. So we have this. We agree here, right now. So it means that when we have this case, already you can tell which one is above, which one is below. Do you agree with me here? You can tell which one should go below, which one should go above. So we can tell me between root of y and y over 3, which one should go here, which one should come here, which one should come below. By looking at this, you can tell me which one should come below. Which one, guys? You see this one, it's saying it's less, right, than x. So it means that it should come below. Do you agree with me there? When I was busy trying to make x up with the formula. You say right, ne?
Yeah, that's correct.
Yeah, and then this one says the root of y should come above. Then that's how we're going to change this one. So just on that recording, I had only considered the ones which they only give us one equation. So this one, they give us 2 equations. So you can try to make them both substitute the formula. This one's just going to substitute here. For you to get the lower one, substitute on this, the upper one, you substitute on that. We say, right, then we see what we get. We plug those values there on y. So now, since that will be the type 2 region, which is this, you can still use this to integrate. It means that now, when you put this, you know that this one is with respect to y, it will be outside. With respect to x, will be inside. Then you continue and do that. So, now let's look at another example.
Okay.
You can also look at the graph as well.
Yes.
Yeah, we
yes.
can also look at the graph. The graph, usually for the graph, what you're just going to do, right? Usually, I don't want it to depend more on the graph. The graph, what you're just going to do, I agree this one was x squared, right? This was 3x. So what you're just going to do on the graph, I agree it was pointing up, right? You're just going to point this side now. Then you change this one. The graph won't change. You just change this. Now, I agree this was this. Now you change it to x less or equals to root of y. We say number, but you'll use equal sign for this graph. Then this one, you change it to this, x equals 1 over 3y. But everything still remains the same. We agree, right now? Yeah, just that. Then when you look at the graph, for the graph, we see here that for y, it's from 0. Now here we need the ones for y, it's from 0 to 9. Then this one for the graph now, it's moving from, we check, it's moving from 3, from this one, y over, since this now graph is y over 3, you write y over 3, up until root of y. You can also use the graph. But if you have trouble with the graph, I just want you to know this, that for type 1 region, you're just going to point up. Because I know the majority are having a problem with the graph. You point up. And then for type 2 region, you're just going to change the arrows this side. Then you also make the other ones with the formula. So simple as that. So both cases, they can lead you there. So now, but if they bring you a question that you see that you find difficulties drawing the graph, for example, you must look at how to draw the graph of absolute value of x. Believe that the graph of this will be something like this. You see right now? So you must look at such cases. They can also bring such ones on the interval. They bring you absolute value of x and so on. So you must look at how do I draw the graph of this and so on. So now when it comes to changing the order, which we've just done there, now we're given this. Sometimes they won't tell you must change the order. You just see by yourself that I'm given this, right? Here it's inside, it's y. So this, with respect to y, it will be a bit difficult to integrate. But then reason being, if I let this be u, right, I derive it. The remaining of x, they must cancel something here. That is the rule, right, of your substitution. It must cancel some y here. So the remaining of that will be 2y over, what is over there? Over what? Over 2. It will be 2y. Let me see that. 2 be not 2y over 2. Yeah, when I derive that, it will be something like this, right? So this will become 0. So this y squared must cancel some y squared here, and we don't have that y squared, so deriving with respect to y first will be difficult. So it means that we must change this order so that we can have x inside, so we can derive with respect to integrate with respect to x, so we can have x there. Things become simple, you say, right? So it means that with that being said, we're gonna write our interval first. We see that this is type 1 region. Then you can draw the graph, or first, before you draw the graph, you could already know what is your type 2 region, because this is type 1 region. You can see x there. So now on type 2 region, I just need to change this to y. This was x, now it's gonna become y. Then this will be x. So let's make this with the formula and see which one we're going to have. We're going to have that x is less or equal to y squared. So between this right, if this one comes here, the one here we're gonna inherit here, you see, right? Then if that comes here, this is what I explained on the first recording. It means that here we're going to inherit this one, you see, right? Ne? So, but if you forget that, you'll see that no man, I'm left with a value here. You just have to inherit it. So let's check that. We realize that this is gonna be less, right? So it means that this will be less than y squared. Then the 0 will inherit it here, right? Then for you to find these ones of y, it's simple, because you already have this. You're going to just substitute this one. When you substitute 0, you're going to get 0. When you substitute that x is 0, you have 0. Then here we don't have any equation, so this one will remain 1. We agree there, right now? So that will remain 1. We inherited that one because we don't have any equation. So it means that this one was going to be your type 2 region. But you can still draw this graph of y equals to root of x. If you don't know how to draw this graph, right, you're just going to use table. When you use table on your calculator, it must tell you which one between. Sometimes I get to see that this graph, this one, is just gonna be the some sort of like inverse of y squared, right? So remember, the one of y squared goes like this. So it's possible for the graph to go like this, and it's possible for the graph to go like this. So if let me tell you this, if these, right, if x grows bigger than y, faster, or it grows faster than y, it means that the graph is gonna go like this. You see, right? Then if y grows faster than x, it will go like this. So when you plug on your table, you're gonna see those values there. When you plug on the table, you see the values. So let's say here I plug root of x, right? That y is equal to root of x. Then I start this from I will start it from 0, because we see that x starts from 0 and y starts from 0, right? So here, since I'm drawing for this one, x starts from 0, so just start it from 0 up until I'll end it at 5. Then I have 1 there. So when we check this, when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 1, 4, 1. So you see that x grows bigger than y. When x is 3, y is 1, something. When x is 4, y is 2. You see, right? So this x grows bigger than y. So it means that this graph is gonna go like this. You see, right? But then we're interested in that. So also, so let me just draw it to be like this. So we see that this one is gonna move like this, right? Then we are told that y is equal to 1. So this is 1. You see, right? So the region here of this will be between this and this. You see, right now? And when we check, this root of x is the lower part, 1 is the upper part. So it means that we're going to shade here. So this is type 1 region. So we're going to point there, right? Because x is there on the interval. So it's type 1 region. So this will be the first part, right? Then we check here. We say that x is from 0. When x is 0 in this case, will be 0. That's the the x axis of that graph. Then we say that x moves until 1. So when x is 1, we can check what is y. Y is also 1. So we see that will be the case. So in this case, we are going to say this. Also the point here will be 0, 1. Because you know that when x is 0, when y is 1, x will be 1, right? So no, this one is not 0, 0, it's 1, 1. When x is 1, y is 1. So this is the case, right? When x is 1, y will be 1. So now we say that for us to draw this region here, again this type 1 region, we see that the region is going to be, according to this graph, x is between 0 and 1. That is what the graph said. X is between 0 and 1, and this is what we see. And also the other one, we see that this is the lower part, right? So we're going to have 12x less equals to the upper part is y. So this is intersecting with the y-axis. So now we have this to say that this is type 1 region. So for type 2 region, we're going to draw the same graph. We have the same graph, y. Now, this is going to point this side. You say right? It's going to point to this side. Now, remember this was 0, 0. This here was 1, 1. Those didn't change. You say right? Then, now the new region will be, this will be x, y. And then we have y here. Now this will be y. Y is moving from 0 till 1. We say right. Then once we have x, then this will be from, this is what? This is 0. Up until this graph now will change to y squared. You say right now. If I make this, or you can make this first the region subject to the formula, which here we got that x is less or equals to y squared. So we know that this part here would be y squared. You say right. And this first 0 part would be inherited from this, which is what I showed you. So you can do both. You still find it the correct thing. You say right. Now you just shade going up. You say right. Shade going up. Because now you're in type 2 region. Change it to type 2 region. Everything remains the same. You just change that. You should have changed it to that. This first region going up, then second region. Yeah, let me confirm if we did that. Yeah, that's it. Before we shaded going to the other side, which is the same thing as what they did. Then the first one we shaded going up, which is the same thing as they did. Here they just changed the interval. You say right. You're the equation to that. And it's the same thing. So now it means that we're going to change this and say this is from 0 to 1, and outside it's y. Inside we say it's from 0 to y squared, and inside it's x. Then when we integrate this, we're just going to have x here. You see that it will become simple, right? Ne? As long as you know how to mess around those intervals. So you can do it in both ways. So if we check here, first we have that as x. So that will be x. And then after integrating there, we plug our, remember, when we plug here, we're going to plug y squared here, and when we plug 0, the other one will become 0. So remember I said that for this to work, your substitution to work, remember when we derive this, we're going to have 3y squared over 2. So that there should be y squared to cancel that y squared there. You say right now, where is it? This one. This y squared should be found somewhere there to cancel out. If we plug back, you'll see that at the end, this y squared will cancel out. We take out it there, 2 over 3, we're left with sine u. Then when we integrate sine u, I've already shown you how to integrate sine. This will be cos negative cos u. So it means that when you integrate sine u, you're going to get negative cos u. So that is why here, when we see we get negative cos u, then from 1 over 2 to 1. So the reason why here we have 1 over 2 to 1 is because when you use substitution, you prefer to say you change these intervals. You say, right? So the question is, how do I change those intervals? Here, x is 0, x is 1, right? So what I'm going to do, I'm going to use this u substitution equation. It's based with y, right? When y is 0, I'm going to plug 0 here. I get 1 over 2. So it means that this interval now will be 1 over 2. When y is 1, I plug 1 there. I get 2 over 2, which this will remain 1. You see, right? Then that's why here, we don't have to even substitute back our u for us to work with this interval. So you'll have 1 over 2. And that will be the solution. Do you agree on this? So I believe that it's simple in this way, right? So that's why if you are able to mess around those intervals, it will be as like that. So here, when you come to A, this is what I discussed there in the group, there in that recording, right? These two. So I'm going to skip these two because I've already made the recording about them and I've uploaded it. I think it was yesterday. These two. So I did that. If you haven't watched it, it means that you must watch it, right? So now we come to double integral in polar coordinates, right? So when we come to polar coordinates, we say that if the integral, if we're given this, and they say that it's evaluated where R is a region, as in the following sketches, right? And remember, you must not forget here that there should be d something. So some of you, when you write the integrals, you forget there that there should be d something, right? So when we have a circle, guys, let me write this for you. This angle will be 0. This will be pi over 2. We've learned this in complex numbers. Remember in set theory. Then this will be pi. This will be minus pi over 2. And when it gets to this part here, it will become 3 degrees. You say right now. So now, when we have a circle, we are going to have our angle being 2 pi. Then, when we have this half a circle, we're going to have our angle being pi. And our radius will depend whether, if it's one graph, our radius will be from 0 till this range. Then when it's 2 graphs, our radius will be from this range till this range. That's why here they gave us 2 figures to say that we're going to work with 2 different figures. You say right now. So this is x squared plus y squared, which is equal to 16, and root of 16 is 4, right? So it means that here our r will be between 0 and 4. Then with this one, first one, it's root of 4 is 2, root of 9 is 3. So our range there, r, will be between 2 and 3. And also our pi will always be between 0 and some angle. So this one is between 0 and pi, because you can see it's only hitting pi here. Then this one, our pi will be between 0 and 2 pi, our angle. So if we know how to sketch a graph, it will be simple for us to change it to these regions, right, of the polar coordinates. So now let's come to this. You realize that you see the first one, r is between 0 and 4. This is pi between 0 and 2 pi. It's theta between 0 and 2 pi. This is between 2 and 3. This is between 0 and pi, which is the same thing there. You say right. So now, in most cases, you'll find this. So when you come to this, we are going to use what we call SOHCAHTOA, right? And so you have what we call Pythagoras theorem. So what the 90 degrees angle says that this will be x. You know, this is the x plane. This is the y one. Then this is r. So without using any Pythagoras theorem, we're just going to only steal this gravitation, right? Then we're going to say that for us to find this, This is the adjacent angle. This is the opposite from this angle. This is a hypotenuse. So sine says that here, according to SOHCAHTOA, sine of theta says that this is opposite. Opposite is y over hypotenuse. Hypotenuse is r. That's why we have this. You see right now. So those you're not supposed to cramp. You're just going to have them like that. And the idea between having this, the idea is so that we can find what is y, because we're going to need to substitute y at the end. If we multiply both sides by r, we're going to get this. You see, and then you find this one, of course. You find that this x is equal to r cos x. Now let's come and see what, remember, if you want to ask a question, you can do that. Let's see when you're given a question. Yeah, we don't need this. Yeah, but you can try to check this for the polar coordinates. They can tell you to state the function for a polar rectangle. So now, but the one which I'm more interested in there is Frobenius, right? But you must know how to state all of them. So now we're given this example. They say we're given this xy. So what I know here is that before we change anything, or before we have anything here already, I know that I must change this. Let me show you this. I must change this. This one is gonna become our x. I'll plug r cos theta. Then our y, I'll plug r sin theta. Then this one will be r dr d theta. So this is what I know about dA. dA is equals to r dr d theta. You see right now, this are equal. You must always know that that's what you're gonna substitute. So this will always be the case. So it means that when I come here, I'm going to say this is the integral. Outside here, we'll see what you're going to have, right? So this will be x there will be r cos of theta, y will be r sine of theta, and the a is replaced by r dr d theta. That's right. So this case of changing to this or drawing the graph, we'll just find these intervals. You see right now, that's the last thing we're left with, to find the intervals. Already you know there what you're going to substitute. X is equal to r cos theta, y is equal to r sin theta. So now we come here. The equation here said, or the question here said that where r is the region in the upper half plane, in first quadrant, bounded by the circle. They said in first quadrant, right? Upper half, first quadrant. So we focus on first quadrant here. It means that when we draw this graph, and here we focus on first quadrant, so it means that this will be like this. And we're given two graphs to be like this, which this is the inside one. The small one will be x squared plus y squared equals to 4. The bigger one will be x squared plus y squared equals to 25. You say, right? So we say that the lower one is the one with 4, the upper one is the one with 25. So the first graph, this we know that x squared plus y squared will be between 4 and 25. Right? So this one's already, we know that here this only occurs when x is greater than 0, when y is greater than 0. You say right now. So here it will be x greater equals to 0, y greater equals to 0. So now here we can change this. Already I know here that my r, I can change this to polar now. I can change this to polar. I know that the root of 4 is 2, root of 25 is 5. So I know here when I change this to polar.
Sorry, Anyalo. I don't understand. Can you please repeat again for that thing already? The x is greater than 0 and y is greater than 0. Like, just don't understand it clearly.
Oh, I can hear they say that this is in the upper half. The upper half is this two, right? Ne? The first quadrant and second quadrant, these are called the upper half plane.
Yes.
But then they restricted us to what? first quadrant. And first quadrant is where x and y are both greater than 0. You say right now?
It's where
X and y are greater or equal to 0.
Okay, yes, yeah.
Yeah, so it means that our x and y, we're just going to label them like that. We say x is greater or equal to 0, y is greater or equal to 0. But then according to these two graphs, again, you remember that the other part, we're supposed to graph according to what we're given here, right? The graph, we check which one is the lower one, which one is the upper one. And in this case, the lower one is this one. The upper one is this one. So 4 will be less, 5 will be above.
Yeah, for that part I don't understand it. I was needing this one now, x is greater than 0 and y is greater than 0.
Oh, I see. Now you understand, right?
Yeah, now I think I understand.
All right. Yeah, so it means that for this one, it means that now we're going to come and say, I want to change this to the other part, right? So first thing which we write here, we're going to replace x by r, replace y by theta. And then first we write the 1 over r, like it's r here, we have r. So we see that r will be between what? R will be between 2 and 5. We agree here right now. And the theta, this one for theta, remember I said that this is 0, this is pi over 2, this is pi, this is minus pi over 2. So this one, it only heads to what? The angle only adds up to pi over 2. So this will be from 0 to pi over 2. You see right now? So this will be the case. And then...
So will I be wrong? Sorry, so will I be wrong just to include this region like this way, not in that format of the equations?
You mean in this, which way?
One in blue, the one you just wrote. I'm including the region in this way, not in the form of the one in black.
Not in this form?
Yes.
Oh, the problem is here you first need to write the region which they're talking about, and then you change it. It's like you're writing this region and then you convert it to the other. It's like we are showing them that I'm moving from this region to this region.
All right.
Yeah. Then for that, so this one you're gonna be using it to draw a graph. Yeah. Or after drawing a graph, you can just point out this ones and say this is R. And then now we change to, we already changed it to this region. The integral that time said that is region R xy dA, and already we found these ones. We see that from this one, the one of the angle, right, will always be outside. R should always be inside. You see right now. So the angle will always be the one to start, and then R will always be inside. So there we had xy. X I said that we're gonna replace it by what? R cos theta. Y I said we're gonna replace it by R sin theta. And I said that the A will replace it by R dr d theta. So this will be R times R is R3 cos theta sin theta dr d theta. So when we check here, integrating this, so let's see if they wrote that so that we can look how they integrated it, but it will be R to the 4 over 4. So you see that they drew this right now. So here you don't have to point anything here, you can just shade. So you shade your graph, and then you see that this is the lower graph, the upper graph. Then you change this to R. This will be R theta. R is between 2 and 5, and theta is between 0 and pi over 2, because here it's pi over 2. This is 0, this is pi. So you see it's between 0 and pi over 2. So it will always be between 0 and something. Unless if it's maybe it's on the second quadrant, this would be between pi over 2 and pi. That's how we need to get familiar with these things. You see, right? If they bring this on the second quadrant, it will no longer be between 0 and something. It will be between this and this. We agree, right? So that's what we must keep in mind. So now we come to plug. We know that x will be plugged as r cos theta, y will be plugged at r sin theta. Then we replace dA as r dr d theta. And then when we multiply those r's, we get r to the 3. And always I said that the one of the angle should always be outside. So, and we know that when we integrated, this will be r to the 4 over 4, because cos theta and sin theta are constants. So now from here, we substitute those, we get this. And this, remember, we know that sine 2 theta will be equals to 2 sine theta cos theta. So if I divide both sides by 2, I'm going to have sine theta cos theta is 1 over 2 sine 2 theta. So you can change that. Then this multiplies out, it goes out as a constant. Now we integrate sine 2 theta. I've already showed you how to integrate this. You're just going to get, you know that if you have sine theta cos theta minus cos theta. So when you integrate positive sine theta, you get negative cos theta. So here it's negative 2 theta over 2, because here we divided by the derivative of the inside. So we plug those angles there. Then we get that. So that will be simple, right? Now we come to the second one. Here we are given this. They say that R is the disk with center, the origin, and radius 2. We say, right, and this one radius is from 0 to 2. So this one, I understand now that the question which we were asking, this one, they didn't give us a restriction. We say right now, they just drew a circle, which is a disk, right? They said this is a disk with center. But then when they give you a certain region, just a quadrant, you're supposed to show that region. You say right now, if they give you a quadrant, you're supposed to tell them, because this one is it's clear what you're dealing with. So you're going to write it that region. So here we see that here x is an element of real numbers and y will be an element of real numbers. In other words, we can say x and y are between, so all they're covered, right? And then now when we check this one, this of x squared plus y squared, this is just a disk, right? So we know that here is just x squared plus y squared is equals to 4. This one is not restricted. So this would be our r. You say right now. So with this one, there's no restriction. So that's why there was no need to write this r. So now we come to this. We want to change this, right? But we realize that this revolved. It's a circle or a disk. So it means that our angle will start from 0 to 2 pi. And our r will be from 0 to 2. You say right now. And that will be simple as that. So when we come here, on x, we're going to plug r cos theta. On y, we plug r sin theta. Here, on dA, we plug r dr d theta. Then here on this interval, we'll start with the angle from 0 to 2 pi. Here inside, we say from 0 to 2. So that will be as simple as that. So it means that when we come here, we're just gonna do that. We plug, we take out r squared and cos theta plus sin theta, cos squared theta plus sin squared theta is 1. So r squared will just give us r. Then we have this, we use by parts. Yes, right. Then you can use by parts to integrate that. You get to the solution. So let's see if we have another example. Then we have a Jacobian transformation. Did you guys do the Jacobian transformation in class? Did you guys do the Jacobian transformation? Usually with us, we didn't do it, right? I don't know if you guys covered it. Did you guys do the Jacobian?
Those one, I don't think they did it. I'm not sure also.
Oh, yeah, because if you didn't do it, yeah, if you didn't do it, it means that we're also not going to do it. But I think those who are doing stats, they might know Jacobian. by now, transformation. Because I think last year was done by this guy, Dr. Deep. So I don't know this year who did it, but with us here, they didn't do it. We only did it in statistics. But the Jacobian transformation is just like we see when you come to this one. What's this one? The critical points. When you come to label the critical points or list and classify the critical points, we have what you call Hessian determinant, or D, where we have to check D of XY. We must check if this is a local maxima or local minima. That one also uses it's some sort of like a transformation, but that one is called Hessian determinant. So it's a similar transformation. The only difference here is that this one is with respect to U, and with respect to V, with respect to U, and with respect to V. Then when you multiply these two, you were going to get just but I don't think they did it, because they didn't discuss any background about it. Yeah, I don't think they did it because they didn't discuss any background about it. Yeah, so I think it's the same thing. So for this, we're going to skip it also if they didn't do it. Also, they didn't classify any example based on this. So with triple integral, it's simple also. This one I'm not gonna do this because it's simple. You just integrate, you plug, you integrate, you plug, integrate, you plug, right? So this is just requires your knowledge of integration. If you know integration, you can do this. So let's look at these exercises. Let's see, this is dz, dy, dx. We are not given anything here, right? So it means that the integral of this, it's 1 there. It's not like there's nothing, there's 1. You see, right? So when we integrate this first, we're gonna get z, then we'll plug those. We come back to see if we can integrate and so on, right? Then also this one. So also here, guys, you can find yourself using this. Let's say you had the circles here, you had the circle and a circle. You would use coordinates, right? So you must make sure for polar coordinates you must have a circle. This one it might contribute to a circle, but this one is not, right? So you can use polar. This one won't contribute, it can use polar. This one also won't contribute. This one. So when you draw a graph, guys, you always draw these ones up here. You see, right now, always draw these ones here and the intervals. You see, right? When you draw a graph, so you're always gonna do that. So you're going to do that. You draw a graph. Even this one, you draw a graph. So let's see this one. This one is what? They said this is 0 y less or equals to root of 4 minus x squared. If I square both sides, this will be y squared plus minus x squared. And this one can contribute to a circle. Yeah. Then you can also check the other ones. This one contributed to a circle. It means that this one will also contribute. So you can change this to polar. Even this one contributes. This one doesn't have a root. This one you can confirm though, but I don't think it can contribute. It will be x. Yeah, this one won't contribute to a circle. So this one can. This one can. I think these ones inside here, they can contribute. So it means that after integrating the first time, you can now change this to polar coordinates. Alright. So you must confirm if they contribute. Yeah, it does contribute. You draw that. Pi, you change this, which is simple as that. Then you apply your integral. Alright. And then, yeah, I think the last thing that will be left with to check here would be the line integral. So we'll create a session where we discuss. So on the line integral, I want us to discuss the theorem, because here they said the theorem will come, and the only theorem we have in this chapter is the line integral. You see, right? The Green's theorem. So if we do Green's theorem, it means that we are set. So the ones who, I don't know if I still have the theorem here with me. The ones who have the theorem can send, right? So that we can look at it on the next part, and then we'll look at how do we apply it. So first thing, we look at the theorem. Secondly, we look at how we apply it. Then we look also at chapter 5. So I think we can do that maybe tomorrow. I'll create a poll then we discuss.